Hi, I'm Antonio Sala, and in this video we'll continue with the discussion of a total least squares case study we already did a video about. We generated some data, we checked that ordinary pseudo-inverse least squares was biased, and then we did some scalings and obtained an unbiased total least squares estimate. However, what happens if the scaling is wrong? Well, this will not work so well. If we summarize the previous video, we were generating data like this with a clean theta given by this model. Clean data were contaminated with an additive noise, measurement noise, with this standard deviation for each of the 5 channels in my dataset. Input noise makes pseudo-inverse stuff being quite biased, but total least squares, if we scale so that the measurement noise in each of the channels is 1, divided by the standard deviation of each of the noises and putting a big matrix with all data in, okay, in such a case, centering, subtracting mean, plus singular value decomposition finds 2 principal components that have a variance exactly equal to the unit noise, so we understand that the underlying clean model would have 0 variance, but unit random noise is added to give this 1 here. So these are kind of 3 excitation signals, and these 2 principal components, we assume they should be 0 under no noise conditions, and that's the clean model. We choose the last 2 columns of U matrix in this SVD decomposition, and if my data are in column form, I assume this is the model. Okay, this is the model in scaled units. I would need to divide by the standard deviation each of the columns of this model to get the model in non-scaled units. That's what I do in mod X and mod Y lines of code. So that will be the unbiased total least squares estimate. Now, let's go to the main topic to discuss in this video. What would happen if my scaling is wrong? Well, bad things may happen. Let us label data wrong, the raw data with no scaling. Why? Because maybe I thought that these data were already normalized to having the same amount of noise per channel. So who knows the additive measurement noise in a particular application. Well, if I get it wrong, for instance, doing this, okay, I will subtract the mean to do exactly the same code as in previous tests. Then, well, this SVD, total least squares, results in this principal component standard deviation. So it seems that there is only one of those components that can be said to be, very small. We are good. We know that there are 2 equations inside, but the wrong scaling means that even if I should have 2 zeros here, noise is multiplied by a large number because this 6 is, comparable to this 12, well, so maybe here we would incorrectly assume that there is only one relationship, one equation in the data, and only one variable could be solved for as a function of the remaining 4 inputs. As we are good and we know that there are 2 equations, I can, it's kind of a lot of imagination. Okay, I will assume that this 5.8 is also small compared to this 12. But, if the scaling were perfect, I would have 1, 1, and here I have 6.7. Well, let us keep it like this and assume that these 2 things found a model, so I get the 4th and 5th column of the U matrix in the SVD because it's the sample of data, it's in a column. Well, okay, this model with the wrong scaling will be this thing. Okay, if I had made any scaling, I would need to express the model in the original units, but to keep it simple, I directly used original units, so I need no further inversion of the scaling, but because there was no scaling at all. So this wrong scaling model is in original units. if I solve for y, for the two first variables by inverting this matrix, then I get this theta that is of course biased when I compare it with the clean theta that I used to actually generate the data. So this is it. If my scaling is perfectly as theory requires, then I get 1 singular values and I get an unbiased total least square estimate. If my scaling is wrong, then, well, I get a biased estimate. So we may think, okay, come on, if we had applied, pseudo-inverse least squares without any of this SVD stuff, we would also have a biased estimate. Is that biased estimate better or worse than this one? Well, let us compare. The total least squares model was the juxtaposition of this. Okay, these are two equations that multiplied by 5 signals are approximately 0. So the allowed points compatible with these models is the null space of this matrix. Then, how can we compare this model good scaling with this ideal model? Identity I minus theta clean x would be really exactly 0. So let us compare the TLS model with good scaling, the TLS model with bad scaling, and the ordinary pseudo-inverse least square model. We will compare that with the ideal model. However, as the models are, in some equations that should be 0, we will use kind of trick for comparisons. For instance, I may have a model y minus x equals 0, the red line. I may have a model 0.95y minus 1.03x equals 0, green line. So I would say that the model deviation can be assessed by computing the angle between these two lines, because the coefficients do not really tell me if the lines are separated. I may have 12y minus 12x equals 0. That is actually the same model. It has the same null space as the red line. So we will compute the angle between the valid regions of the 5D space dictated by our different models. So let us see. The angle between subspaces generalizes to this idea of the angle between lines, and that's done by Matlab with the command subspace. So the null space of the ideal model would be the best model we wish to obtain. Then the wrong scaling model had an error, let's say, of 3 degrees. The unbiased total least squares with good scaling had an error of 0.1 degrees. And the biased least square model had an error, an angular error. Don't know what it is, but with one number, this angle, I get an intuitive interpretation of what I am doing. We can see that the offset is 0.1 degrees, it's almost nothing in the good model, but the total least squares model with the wrong scaling has actually a larger deviation with respect to the ideal stuff than the theoretically biased least squares. So this is the conclusion. A wrong total least squares scaling may give me a worst model compared to the ordinary least squares. In fact, this angle is also scaling dependent. So maybe some care is needed because, okay, if I expanded and multiplied by 2 the x-axis, then those angles would change. So, okay, this is just scratching the surface of the idea on how to summarize in one number the difference between several models given in, implicit equations, null space. At the end, a wrong TLS scaling may give worse results than the plain least squares. Whether 3 degrees of error versus 1 degree of error is important or not, well, it may depend on my applications, on the precision requirements, and perhaps I should use some sort of validation data set, But To conclude, if data are abundant and generated in accordance with the theory, and they know the measurement noise variance, then total least squares works as theory predicts. However, if I have not so many data, or I make a wrong guess with the scaling, then TLS may be biased. And not only my model may get biased, but even I may conclude a wrong number of equations. So even if my data had 2 clean equations inside, I would have been very tempted with the wrong scaling towards saying that there is only one equation relating these 5 data in an actual application. Well, we finished with this. Thanks for watching.